Hello, it's Keith here, and this is lesson 95 of the platform-specific series of my Z80 assembly programming tutorials. We're looking at the ZX Spectrum today, and we're looking at my MaxTile software tilemap. So MaxTile is a multi-platform tilemap. It runs in basically the same way in all these different systems, and I've ported the same example with relatively few changes to every system. Just a few things like the pattern data need to be changed, the main code stays the same. So here is the example. We've got a character moving around the screen, and we have things like X and Y flip and X plus Y flip. We also have clever tricks that will hopefully save a bit of processing power. If I can get my mouse cursor working properly, I cannot. We also have clever tricks like fast-filled tiles filled with 2 bytes to save some time. Double height tiles, these ones are stretched double height, and that saves some source bitmap data, things like that. So we've got various other tricks included in the code, and so we're going to take a look at that code today. Now MaxTile is a little bit complicated because of all the tricks that it has, but as a handy hint, if you don't want to use MaxTile, you can actually use the basic code within this example and just use it as the sort of template for a bitmap drawing example of your own, or you could use the tile draw routine within your own tilemap code, and that will work just fine. Now, there are 2 limitations to today's example. One is a limitation of all my ZX Spectrum examples, and that is the movement row is in full 8x8 pixel blocks. There's no half pixel block movements, and the reason for that is that the code is optimized vertically for the memory alignment of the screen, and horizontally without bit shifting you can't move 4 pixels on the spectrum because 1 byte contains 8 pixels. So for speed, that's a limitation of this version. Now I do have an alternate version of the code which uses different colors for different tile blocks. They're all the same color in this example, but we'll look at the other version next time. Anyway, let's go over to the code. Let's see what we've got. Okay, so this is the example file that we're running today. There is also a second file, which is the actual tile drawing routine. So we're going to look at this file first. Now, MaxTile uses a cache to remember the changes that need to be drawn to the screen to reduce the amount of flicker. It doesn't use a double buffer, not by default, and that's because some systems aren't very good at it. Like the Spectrum on the old 48K could only do a double buffer by using LDIR to copy the memory. The later 128K versions could do hardware buffer, double buffer, but as I say, a lot of systems couldn't do it, and even the ones that could may not have the memory to do so. So we use these caches, 256 bytes each. They do the thirds of the screen. We also have a 256 byte lookup table, which is for the Xflip effect. We don't flip the pixels in real time. Horizontally, it will be too slow. Vertically, we do, but horizontally will be too slow, so we use a lookup table. Now, some of our draw routine, we draw in the entire screen, use the screen-based variable, and this defines the start memory address of the screen. The simulated sprites use the tile code as well. However, they've got their own get screen pause function that does that. Now, one thing that's worth bearing in mind on this system is we're using IX and IY as part of some of the subroutines, and the Spectrum code, I think it's the IY register. It might be IX, I forget, but basically you can't use those, or the operating system interrupt handler will crash. So we actually disable interrupts as part of our code because we use stack misuse, where we use the stack pointer for purposes other than a stack. We use it for reading, but usually I would enable interrupts, but on this system we don't. So this do enable interrupts macro has nothing in it. Usually it would have an EI command in there, not on this system though. Now, at the start of our code, we're doing a couple of things. Firstly, we're clearing the color data entirely to color 7, which is this sort of darkish white. That's because we have no other color code in this example. As I say, the other example will have some color code. And then what we're doing next is we're defining the lookup table. This is the Xflip lookup table. So this has 256 bytes, and basically what we do is we use the L part of the HL pair as the source byte that we want to flip. We flip all of the bits by simply shifting them from the right of A into the left of B, and then we write B to the destination. And so what this means is that if we load H with the address of the lookup table and L with the source data we want to flip, if we then read in from H and L, we'll get the flipped equivalent. So that's what this lookup table is building. So that's that. Now the other thing we're just going to quickly look at is the bitmap data. So here is the pattern data for today's for the tile patterns for today's example. Now each one is 8 bytes. This code MaxTile was optimized for 4 color tiles, so that would be 16 bytes. And so there's a few little shifts there in some of the code because it was optimized for the other size. But here are the memory addresses for various offsets, and we're just positioning our bitmap data in the right positions for the various characters tile numbers for that multi-platform code to work correctly. Now the rest of the code is in this MaxTile normal routine here, and that's what we're going to look at here. Now, all of the coordinates within the MaxTile routine and all of my modern tutorials use logical units, which is a nice, clever sounding way of meaning pairs of pixels. So because a lot of the systems I work with are 256 by 192, but I use 1 byte coordinates on 8-bit systems, and so if I used a 256, 0 to 256 as pixels, that would mean that I wouldn't have enough for any kind of clipping of the edges of the screen. So I use pairs of pixels, so the logical screen is 128 logical units wide, 256 pixels wide. So that's what the X and Y coordinates passed to this will be in. Now, because of the way the spectrum screen is laid out, basically, if you think of this as being the 16 bits of the VRAM destination, the bottom 5 bits are the X coordinate, the next 3 bits are the bits 3, 4 and 5 of the Y coordinate, bits 6 and 7 of the Y coordinate are all the way up here, and bits 0, 1 and 2 are here in the H part. Now that is actually quite convenient for us, and that's part of the reason why I'm always moving in 8x8 pixel jumps. A little bit jerky, but nice and fast. You see, when we want to move down a line within an 8 pixel block, we just increment H, very easy, and when we want to move across the screen, we just increment L. Now, if we were doing if we were breaking that 8 pixel aligned boundary, then we would have to start maybe changing these bits, maybe changing these bits. A little bit tricky. But basically within this code, what we're doing here is we're taking the Y coordinate here, and we're converting it to a line number, and then we're taking the X coordinate and we're converting it to a byte, basically, so we're converting that to 8 pixels. And then we're taking the various bits of that line number and we're shifting them into the correct positions for the H and L pair. Our screen base is 4000, so we're loading that in here. Now, actually thinking about it, these lines here aren't really needed for this version, for this example. I could actually remove these, but we'll leave them in anyway because maybe I'll reuse this code later on and wonder why it doesn't work. It does happen. So yeah, keeping a few extra lines of code. This code will only be executed once every time a sprite is drawn anyway, so it's very, very infrequent code. The draw tile routine is more heavily optimized because that's run for every single tile that's updated on the screen. Okay, now when this code is executed, the calling routine will have already shifted one of the bits out of the first byte of the tile number. Now, tile numbers in the tilemap use 2 bytes, and the bottom bit is the update bit, which denotes if that tile needs to be redrawn to the screen. A 0 means no and a 1 means yes, and so that bit has been already shifted out, which is why I've put it sort of outside of the byte here. So that bit has been already shifted out, and that's because we want to move a 0 into it if we are actually running this code at all, because we're running this code, that update flag must have been 1, it now needs to be 0. So what we're doing here is we're testing the next bit, which is the program bit here, and that defines if the advanced code is running. The purpose of this, it's kind of like a tree structure. Basically, the purpose is to get to the normal code, the unflipped basic tile code, as quickly as possible, because that's the most likely we're going to want to use. So if that is a 0, then we're going to carry on, but if it's a 1, we will branch to the advanced code. Now, if it's a 0, what we're doing here is we are shifting a 0 back into that byte in our accumulator and shifting that back into the tilemap, effectively clearing that bottom bit of the update flag and writing it back into the tilemap. What we then load is we're loading the high byte, because there's 2 bytes for our tile definition, and because this was optimized for 16 byte tiles, 16 byte patterns, that's 4 color ones, the bottom 4 bits are now ignored, and so that would effectively have multiplied us by 16 automatically. We only need to multiply by 8 those. So what we're doing here is we're shifting H and L to the right by 1 bit here. We're converting that value here to a multiplication by 8. We then add D and E. D and E, when this is executed, will be our tile source pattern data. I should have said as well, BC is the pointer to our tile map data, so that's our tile data. But yeah, we're adding D and E here, and that is basically selected the source pattern data we want to write to the screen. We're adding that to H and L, but we're then transferring H and L into the stack pointer, and that's this stack misuse, and that means that we can pop data from the stack, and that is now the pattern data we want to draw to the screen. Now we're now shifting into the shadow registers, and in the shadow registers, H and L is the pre-calculated VRAM destination, which will be calculated with either get screen pos or via this sort of defined screen base, depending on if we're drawing the background tile map or a simulated sprite. Okay, so that's what will have happened here. Now what we're going to do is we're going to repeatedly pop DE and then write that to the screen. So that gets 2 bytes, 2 lines. So we write the first line here, move down the screen, write the second line, move down the screen, get 2 more bytes. and we keep doing that until the end. Now at the end of this routine, it expects that the HL memory address will be reset to the original starting position. The code that runs this, the multi-platform code, does have a few little extra modules to move across the screen by inking L twice on the spectrum, and down the screen by effectively, on this system we will basically update these bits here and these bits here. So that will be done by the rest of the code. So here we need to reset H, and the way we're doing this here is we're loading H from C because we backed up H up here, which is a bit quicker than doing a subtraction from 7 there. So that is the most simple version of the tile drawing routine, and all of the other versions are some kind of enhanced derivative of that. Okay, so the advanced code does all of the other versions, or at least it passes execution to the other versions. So what we're doing next is we're checking these two bits here, X and Y, and these are the X and Y flip bits. Now if both of these are 0, then this is what's referred to as a custom program. Now that will either be a solid fill, a double height, or the final one is a transparent tile. Now there is a pseudo transparency, although it won't look very good on the spectrum. That is a transparency, right? Basically the way the transparency works is if all of the if an entire byte is 0, then it's not drawn to the screen, but on the spectrum, because an entire byte is an entire line, there won't be many cases that is the case. It works far better on the CPC, where there's 4 pixels in a byte, and that does give an approximation of transparent edges. It does work quite nicely, and that's what Chibi Akuma's My Game did. So but yeah, it doesn't work so well on the spectrum with 1 byte containing 8 pixels. Anyway, that's branching out there. If we get to here, we're doing some kind of flip. So what we're doing here is we're clearing that update flag here. We're then loading in the 2 bytes here, converting it again, multiplying effectively by 8 here, adding the DE source, moving to the stack pointer. Now what we're going to do then is we're going to decide which flipping version we want to do. So we're checking the Y flip flag here and branching out if the Y flip flag is set. If it's not set, then we must just be X flipping. Now how do we X flip? Well, we use that lookup table. We're going to use B and C as our lookup table pointer. So we load B with the address of the lookup table and C with the byte we want to flip. So in this case, first E, we read in from BC right to the screen, and when we read in from BC, we're getting the flipped equivalent of the byte that we put into C. So that is now X flipped 1 byte. We move down the line, do the same again. We keep doing that until we get to the very end. Now, last time we used C to restore our H register, but we can't do that this time because we've used B and C for other things. So we're subtracting 7 this time, moving us back to the start, and then we're done. So that's the Xflip version. What about Yflip? Well, Yflip's all the way down here. What we're doing here is we're checking the Xflip flag, because if the Yflip flag is set and the Xflip flag is set, we're using the XYflip version. So we can do all 4 possible flips: no flip, Xflip, Yflip, X plus Yflip. So here is just the Yflip. Now Yflip doesn't need lookup table. All we do, we read the data in from the source, normally draw backwards on the screen, so we draw from bottom to top. So here we're moving to the bottom of our tile, and then we're popping DE and we're writing those to the screen, moving up the screen instead of down. Now at the end we don't need to restore H at all, because we've actually ended up back where we started, because we added 7 at the start, we've moved up 7 times, we're back on that first line again. So very straightforward. And as I say, this is why I'm keeping that limitation of moving in 8 pixel jumps. It's a quite jerky movement. It might not be appropriate for all things, but it makes this code very easy. Otherwise, halfway down here, I'd be having to check if we'd gone over a boundary and check which kind of boundary it had gone, and that would make the code much slower on systems like the CPC. When I've actually added code to do that, what I've done is I've created a whole second copy of the code with the extra checks in. But the problem with the Spectrum is that would work fine for moving down the screen, but what about moving across the screen? Because that's got a problem of you'd have to do bit shifts, and so do you have a second lookup table? I guess you probably do. So yeah, it would have added a lot of extra complexity, and it wasn't appropriate for the scale of the example I wanted to do here. Okay, so that's how we do Yflip. How do we do XYflip? It's very easy. We just do both tricks at the same time. So we move to the last line of our destination tile. We load our lookup table into B. We read in a byte from DE, and we read it. We set C to the byte we want to flip. We read in from the lookup table, write it to the screen, but this time we move up the screen after each time. So as I say, both effects. Of course, Xflip is going to be slightly slower than uncolored. Yflip, I don't think it's going to be really any slower at all. I mean, all there is an extra add 7 in there. You won't notice that, I don't think, not significantly. So that's it's going to be very fast indeed. But the Xflip will be a little bit slow, but this is certainly the fastest way of doing it. You don't want to try real-time bit shifting 8 bits around. It would be far too slow. Okay, so what about our custom tiles? Well, we've got a few options here. So we've got fill, which is filled with just 2 bytes. We've got the transparency and empty, which is, we'll look at in a moment. And the final one is the double height. So we're clearing the update flag here, and we're getting the 2 unused bits from the first byte. At this point, only these 2 bits of the first byte are unused, and so they actually become the H byte. The second byte, which is normally the H byte, becomes the L byte with these custom ones. Again, this is the simplest way of using the bytes available within the 16-bit value for the tile numbers. So what we're doing here again is this time we're multiplying by 4 because we're going to use each line twice on the screen. So there's 8 lines on our screen, but we're only going to use 4 bytes because we'll draw each one twice. So that's what we're doing here. We've got get that source address here. We pop a pair, but this time we write the E byte twice to the screen, then the D byte twice to the screen, and we pop another pair, E byte and D byte. Now, this was originally designed for the Amstrad CPC, my game Suck Hunt. I had a silly little introduction that was a parody of Operation Wolf. I had no memory left and not enough for the tiles that I needed to do the parody. And so I came up with a very crude, simple solution, which was, well, I'll just use tiles. I'll just do all of the graphics, but I'll just halve the height and I'll draw each line twice, and it halved the memory, made it very, very convenient. You could hardly tell the difference. So that's why it was there. It made a lot of sense for the Amstrad CPC. Maybe not quite so much for the Spectrum, but it still will be slightly faster because we're using each popped byte twice, so it will still be a little bit faster. But the fastest and most important is the fill. Now, if we want to fill areas of the screen as solid colors or checkerboard patterns, the fill will help us out. And because this uses the same 2 bytes for every single line, this will be very fast indeed. Now, in this case, we are not multiplying the source tile number by anything. That's because basically we're using just 2 bytes from this pattern data, and alternating versions, offset 1 will use off 1 plus 2, and that will give a nice effect. So using these 2 bytes here would give a nice effect, but also using the odd pair there would also give an interesting effect. So I'm sort of leaving that in. We could have multiplied by 2 here because we were using 2 bytes, but I thought not multiplying by anything and just using every possible byte combination was worth doing. So that's what we do here, and basically all we do is we pop the 2 bytes. The first line we use E, the second line we use D, but then we don't get any more data. We just alternately use E and D for each line. So very simple, very, very nice effect, very fast because only 1 pop. I guess you could even argue that maybe it wasn't necessarily worth using the stack misuse here. I'm not sure on the speed on that, but it's sort of standardized for all of the others, so I've done it anyway. I'm not quite sure on which would end up being faster. I think maybe stack misuse would actually still win on that, but anyway, it's certainly very, very little in it if there's any difference at all. Anyway, the final one is the transparency. Now, the first transparent option is actually if the high byte is 255, then this tile isn't drawn to the screen at all. Now, if you look around the feet of that character there, you'll see that there is no actual data being drawn to the screen there, but there are actually tiles there, and those are completely transparent tiles defined by this 255 byte here. Rather than doing a CP255, we do an INK because that would roll 255 into 0, and that means we can do that means the 0 flag would be set. It's 1 byte less than doing a compare to 255, so that's why we've done it there. It's also slightly faster. So we're assuming that's the more common case. If we get to here though, it's not 255, so this is a tile number that we're going to draw to the screen. So we now convert that 255 back to the true value, and then we load it into L. We've got the 2 bytes in H already, and we're multiplying by 8 again, and we're using the same pattern data as we usually do, so we're adding D and E again. So our pattern data is now being loaded into the stack pointer again as usual, and then all we're doing here is almost the same as our usual draw routine. However, this time we're loading the accumulator with a test value, and I'm using the value 0 here, and what this means is if the byte we read in is equal to 0 or equal to A, then we're going to skip the draw to the screen, and so we've got all of these skip routines here, but we're still reading in the source data and moving down the screen as usual. And so what this means is if a line of our tile pattern data is 0, it won't be drawn. Now the reason I've loaded this into the accumulator like this, and rather than an X or A or something, is because I'm imagining you might not want to use 0 if you wanted a tile to be mostly black, but you still wanted this transparency effect. You want to compare to something other than 0. I used a kind of vertical strips pattern instead of 0 in some of my sprites in Chibi-Akumas, and so in anticipating that might be useful, I've coded this accordingly. Anyway, that is the final version of the code. Now, as I always say with my tutorials, go to the website, download the source code and the build scripts, and you're always welcome to do anything you can with them that you get benefit from. So use them in your own code, even if it's commercial. Take them apart, use bits of them, use them in learning, whatever you can. You're welcome to do so. You don't even need to give me credit. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.